Hello everyone, my name is Peter Schaknat. I'm the Managing Director of Schaknat Electronic GmbH, and today we're optimizing a Scania 143 500. We have a very special vehicle here. As you can see, it's a beautiful 143 series Scania from the 500 series. You can see it yourself, it's been really excellently modified. People often ask us, do you work on older vehicles? These were the first Euro 2 and Euro 3 vehicles with electronic injection. That's why we said today we're going to make a video with something a bit older. Just briefly, for those who are really interested, you can see it here at the front on the Scania. It's called 143, so the 14 stands for displacement, meaning 14.1 liters of displacement. The 3 stands for the series. Scania then started with the 1 series, 2 series, 3 series, and 4 series. Then the first R models came out. So this is now the 3 series with a 14-liter displacement. M stands for the chassis. That's a medium chassis, so the medium frame. And you can see the power, 500 horsepower. Back then, the engines or model ranges were available with 8.5-liter engines, 11-liter engines, and these 14-liter engines, and with 400, 450, and 500 horsepower. So today we already have the most powerful one here. The customer owns the truck. It's a bit of a collector's item for him, and he has customized it in a very special way. You can see it. We'll walk around it again. The truck now has 1.6 million kilometers on it, and the engine is now completely overhauled. I also overhauled it once and said I wanted to do something good for the truck. I want to take another look at the intake rail. I want to use it from time to time for trucker meetups or maybe occasionally for a tour. That's why I said I want to check again what the truck is like now. Is the injection system still working properly? Is the boost pressure still okay? We'll check all that again on the test bench. You can really see how well the truck is performing. Originally, as I said, it should have 500 horsepower and 1,400 Newton meters of torque. The other guy has already strapped down the truck. Today, we are once again measuring the rear axle, and then we will take a look at the input strip together and optimize it. As you may know, the very first EDC series, that stands for Electronic Diesel Control, made use of the Bosch MS5 control unit. Those were the most common variants available back then. There were even those chips you could actually swap out, the ones known as the e-brake. Those are really small data sets, there really isn't much in them, but those were already the first electronic injectors. I learned on those control units. That's where I learned how to solder too. So for me, it is something truly special to have such an old car here with us once again. Let us see what we can actually find out, and let's just be pleasantly surprised. You can see it here again. We've connected the exhaust extraction system. You know, Euro 2, Euro 3. If you let them run for a bit inside the hall, you notice a bit of a biting smell. You can tell that cars were still allowed to stink back then. For the measurement, the exhaust extraction is really important. You can see here from the frame, everything has really been restored. It's really beautifully done. Everything here is painted. That's why we said, we'll be careful, especially with the tie-down straps, so we don't damage any paint anywhere. So, really a beautiful car. I would have loved to have a 3 series scanner too. I have my 4 series Hauber, you all know it. I got it for myself, but I also looked for a long time for a 3 series scanner or 3 series Hauber like this. But getting cars in this condition nowadays is almost impossible. So, really a beautiful car. That's why I'm really looking forward to it. Alright, then I'd say Andre will now do the initial measurement. The old engines are industrial engines from the industrial series, as people used to know them. A modern diesel engine is more about low-end power. People want the torque at the bottom end. With the old industrial engines, those who were 3 or 4 years old back then know that you have to keep them at high revs. That's also the case with their fuel consumption. The customer also mentioned that the vehicle's fuel consumption is relatively high, and on top of that, it genuinely lacks torque at the low end. That's why we said every revolution needs a fill. Low RPM means low fuel consumption. Now, when we look at the initial measurement, I would make sure to give it plenty of torque at the low end, because these cars can quickly save 3 to 4 liters of fuel if they have enough torque down low. All right, I think I've explained enough about that now. So I'd say let's start the initial measurement and then we'll see each other at the monitor. We're going to do the initial measurement now. You can see it for yourselves. The old transmission is basically a 3-speed with a splitter, so a big range and then split up and down. So basically you shift up 3 times, multiply that by 4 and you get 12 gears. Now we're measuring again in direct gear. Direct gear is 11th gear, which is basically the 6th in the lower range, so 1 split down. So then I'd say my hood has that too. By now I'm getting along pretty well with the transmission. Let's get started. But that was truly real truck driving. For that time back then, the first ones came out in 1998. For its time, the features it already had were impressive. Really a cool vehicle. You can see all the EDC displays here with the retarder, even just from the levers. It's really well done. Let's slowly rev it up. The extraction system is included as well. We're accelerating out now. Here's the speedometer, and here again is the tachometer. We're just going to do a measurement now. I've calibrated the speedometer to 1000 RPM. We'll take a look at that together in the diagram. You'll notice it right away in the measurement. The old engines hardly have any torque at low revs. It's completely different with the new ones. At 800 to 1000 RPM, they already have their maximum torque. We can film it briefly now. I'm going to break it down now. I'm really going to break it at 800 now. You can see here 800 is the yellow area, and the green area where I only start at 1200, that's where the new trucks actually already shift up. Now let's go ahead and apply the brakes lightly. You notice now I'm building up the torque. Now the engine is working and now I'm releasing the brake. Now we're going full throttle. You can see it takes quite a while for it to get going from the bottom end. Now you can also hear the turbo. Now you can feel in the green area that it has its power. Now we rev it up to 2200. Then we make sure to hit the right point when disengaging the clutch. Now we let it coast. By coasting, we determine the power loss. We measure the torque at the rear wheel. Through this coasting process, we measure the power loss. What is lost in the rear axle from the engine to the transmission, that's what we lose there. These are always calculated values, but they fit. It's a useful calculation. Torque times RPM divided by 9,550 gives you kilowatts. Kilowatts can be converted to horsepower by multiplying by 1.36. That's how the power is determined. The only thing that I can actually measure on a truck is the amount of torque at the wheel. Everything basically starts from this factor. Now if we take a look at the display, we can see that this is the pure wheel torque. This measurement was taken in the 2 higher gears, and it's important to note that the 2 measurements were identical. Between 1000 and 1200, there's nothing at all. And from 1200 it starts to rise, and the truck actually only reaches its maximum torque at 1500, so relatively late. And as you can see, it only starts to drop off at 1800 or 2000, so the power band is actually somewhat shifted. If you're familiar with the new modern trucks, let's turn off the engine. And that's exactly what I was saying earlier. We want to improve things at the lower end so you can drive it without having to shift all the time, so you can also upshift earlier. Because in the end, especially when I'm coming out of roundabouts or going uphill, I want to be able to lower the revs without having to shift back and forth too early. Of course, both the transmission and the engine, in terms of RPMs, what you shouldn't forget about the old engines is that they were basically designed for industrial use, for industrial series. The entire water pump cooling, lubrication, the oil lubrication, all of that is not actually designed for lower RPMs. So if I take an engine like that and optimize it, give it nice torque at the bottom, but always push it from 800 RPM, then I'm going to overheat the engine. because at higher RPMs, the water pump and everything else work faster, so you have to be a bit careful with that. There are some old rules for engines for the 3-cylinder and 4-cylinder. You shouldn't go full throttle below 1000 RPM. Low load and low RPM is fine, but if you're really going uphill, I always tell my customers, to ensure proper cooling and lubrication, it's better to shift down a gear because that's simply better for the engine. It uses a lot more fuel, but the engine stays intact. You don't keep the engine intact otherwise, and I think that's worth more than that extra liter of fuel. All right, then let's take a quick look at the monitor, and I'll explain the diagram again. Then we'll come over here and rewrite the EEPROM. I can quickly show you that, and then we'll already see each other at the baseline measurement. We've now completed the initial measurement. Let's take another look at it together on the monitor. As you saw in the truck, I also briefly showed you the RPM range from the bottom to the top. I think maybe it wasn't quite as clear in the truck. You can see it here again at the bottom. We have 800 to 2200 revolutions per minute. On the left here is again the horsepower axis or the kilowatt axis, as I mentioned. And over here on the right is the torque, the Newton meter axis. You can see it here now. This is exactly what I was talking about. At the bottom is the wheel speed. The wheel torque is shown, and at the top the engine power is extrapolated. The upper curve is the horsepower output or the converted kilowatt output. You can see here this is exactly what I said and what the customer also complained about. Between 800 and 1200 revolutions, in that range, let's say, the performance is extremely poor. I also noticed this at the trade fair, and it takes an extremely long time for it to get up to speed. Once it hits its sweet spot, it moves forward, but of course that's also when it consumes more fuel. Because ideally, I want to operate the engine in the rev range between 1000 and 1500 RPM, but since it doesn't have the required torque at the lower end, I'm always forced to downshift to a lower gear. The customer lives in a pretty mountainous region. He also occasionally drives with a tipper using the car. With that kind of terrain going up and down, I'd say if you tune it properly at the lower end, you can easily save 5 liters. And especially nowadays, saving 5 liters of fuel is really significant. We need to enrich the mixture a bit at the lower end in terms of injection. Also adjust the boost pressure a little so that, especially in that range, let's say here, it just becomes stronger in that area. At the top end, because of the exhaust temperature, I wouldn't make it too powerful because, as we said, we want to optimize the engine, not ruin it. This is the car that has 1.6 million kilometers on it. The engine has been overhauled, basically rebuilt, pistons, liners, everything new. But of course, the customer wants to enjoy it for a long time to come. That's why we don't want to overdo it. But of course, it should also be efficient. So I'd say, let me take you inside for a moment. I'll show you what an EROM looks like, how something like this is programmed, what such software looks like. Then we'll put it back into a control unit. And then I'd say we'll go ahead and do the baseline measurement again. Here you can see the control unit. These are Bosch MS5 control units in the old 3S engines. As I said, these are the first EDC control units. And so this is precisely where all the intricate soldering work really comes into play. You can see here, for example, you still have those big soldering points. These control units are still easy to repair. And you can see back here, I don't know if you can make it out on camera, this is a double layer circuit board. There's a layer on the bottom and one on top. Basically, there's a kind of magnetic tape inside where the connections run from the top to the bottom. These control units also tend to break, but we repair them too because they're still easy to fix. Just so you know, if you've ever seen something like this, these were actually the very first engine control units. Always be careful with that as well. Static electricity. Make sure to ground yourself briefly beforehand so you don't fry them, because that can happen very quickly. This is the EEPROM I just removed. You can see it here. These are the so-called DIL components. These are the little pins you can see here. This is a real chip. When you remove it, I've already socketed the control unit. The advantage of this is that for customers who might get a classic car or want to restore something, or if they want to do some work, I always go ahead and socket the control units. That way you can basically go ahead and swap out the chips. This allows you to use the original EEPROM just like I'm doing for the customer now. Then he can ultimately decide for himself which particular fuel will work out best for his needs. As you can see, this older version from back then was still equipped with UV erasable chips. On the chip itself, there was a small viewing window that allowed you to see inside. The data stored on the chip could be erased by exposing it to ultraviolet light. This was typically done by placing the chip inside a small dedicated box where the memory was then completely erased by the UV light. But now these are permanently installed. I'm keeping the original EEPROM. Of course, that way the customer can always switch it back to the original. We're going to program it now as well. You can see here, this is my EEPROM. These are also the notches. This is really old school. You don't see this anymore today. That is where the term chip tuning originates from, because you would have to swap out this one particular chip. You see, you plug it in here. So you close it here, then it's in, and then I plug it into the PC and read it out. I've already done that so far. You can see here, I've already pulled up the data set. For most people, this will just look like hieroglyphics. As you can see, this here is the entire memory module, just so you have a sense of scale. What we have in there now is 8 kilobytes. A contemporary engine control unit, like a Bosch MDN, for example, in a new MAN truck or a new Scania truck, now has around 8 megabytes of memory, so 8 kilobytes versus 8 megabytes. That is obviously a very significant difference. That's due to everything related to the new Euro standards. In today's vehicles, many sensors are used. For example, when I press the gas pedal, within milliseconds it checks all the sensors, exhaust sensors, boost pressure sensors. It calculates the injection and then uses lambda correction to determine the optimal amount. So it complies with the Euro standard and the car doesn't produce soot. Older vehicles didn't have this. So as you can also see here, we have 65,535, and these are all in fact empty maps. So for the control unit, if you look at it more closely and in a two-dimensional view, you can see below that everything that is colored green here, as well as the red, is shown. That is the only part that is populated, so you can see that the control unit, even though it still has 8 kilobytes of memory, is almost completely empty. So optimizing the software was a relatively pleasant experience, and it still worked pretty well. I reprogram it now, change the maps that are in there a few times, then go back and burn it back on here. This device is what you call an EEPROM burner, so you just write it back on, then install it here. You can see here it's socketed, which makes it easy to replace. I also wanted to quickly show you this. This series of chips here I can take out again. You can see it here. This is basically the soldered through part. You can see from the plug-in chips it fits exactly. I soldered the sockets on and then I plug it in from the inside. And then we can already do the output measurements again. I'm going to set the customer up for about 350 to 400 Newton meters now. And I said, let's optimize between 60 and 80 horsepower. As you saw, the engines do vary a bit. We just had an initial output of just under 1,950 Newton meters and 470 horsepower. But that's good for a 1.6 million euro overhauled engine. That's why I said, let's set it up properly now and then we'll see it on the monitor. We've now done the output measurement. So the truck ran really well. You could immediately tell during the measurement itself that there was a completely different kind of power down low. Let's take another look at it together now. As you can see here, we originally measured 496 and 1960 Newton meters. Originally, the truck was supposed to have 500 horsepower and 2,140, according to what they specified back then. So we were already about 200 or 180 Newton meters short in the original state. You can see here from the output, we have 547 or 548 horsepower and 2,312 Newton meters of torque. So you can see we hit the 350 Newton meters pretty much exactly. You can really feel it, especially down low. You can see the curve here. I've deliberately left out the wheel power graph here so it doesn't confuse you, so you can really see the before and after. I see between 800 and 1,200 revolutions. Here there's an increase of almost 400 Newton meters. That's something the customer really notices, of course, because it lets them shift up earlier. I can't change the basic character of the engine. I can't just say we'll add 800 Newton meters down there, because the engine simply can't deliver that. The turbo has a certain amount of inertia. It needs a certain engine speed to get going, so it can really build up boost pressure. If you make it too strong at low revs in terms of injection, you'll get the effect that it smokes like crazy. And of course, then we also have the problem that it tends to you have to find the right lambda correction value so that it only produces a minimal cloud when accelerating out, but then the combustion becomes clean again. Because of course fuel cools, fuel lubricates, but too much fuel also makes it hot. So the most efficient way is to briefly enrich it so that it cools down properly. This is important because, as I mentioned, these engines are also well known for having issues with head gaskets, that the studs have a tendency to break off because it gets too hot, and I can counteract that. When a gear shift happens, you get a brief puff of smoke, and then it runs clean again, which also cools the engine for a moment. So, as I said, I think the result is great. I wouldn't change anything else. You can see it, 548 horsepower is a good ratio. Originally, it was supposed to have 500, so we're 50 horsepower above the original value. The customer said he wants to keep driving the car for a long time. That is our ultimate goal, to optimize the car, not to ruin it. I will show the customer the diagram and give him a few helpful tips on what to watch out for when shifting up and down. Although the driving challenge scanner knows these cars very well, he already told me beforehand where the weak points are. That's why it's always good when customers tell us something, then we can address it specifically. And I always say individual engine and transmission optimization. You can't optimize the transmission, it's a manual, so the driver has to optimize himself. But we can preset the engine performance with engine torque so that the engine becomes elastic in the optimal RPM range. You can see it here briefly. At the top, we're at 1900, and then we drop down. You can observe it. The curve becomes more linear at the very top and then begins to decline, especially because of the exhaust temperature, so that you can't over-rev the engine. Well, I'm really happy with the result. I'll talk to the customer again in the next 4 to 6 weeks, and then we'll see what happens with the fuel consumption. We've reached the end of our video again. I really enjoyed it today. As I said, it's from my old school. That's where I learned it, especially soldering. Desoldering EPROMs, soldering in EPROMs, that's something I used to do a lot. I learned radio and television technology, electronics technician for devices and systems. Nowadays, hardly anyone solders anymore. Most things are done by reading out software via OBD, but today you just got to see it for yourselves. That's why I wanted to show you today exactly how this whole process works with the older models. So, as I said, if you're interested in this topic, feel free to check out www.schaknat.de. You can also give us a call. We'd be happy to give you personal advice, especially with these models. There isn't much left that can be optimized. I know myself that enthusiasts who want to keep their cars for a long time are happy to invest more money so that the engine runs smoothly and the fuel injection is properly adjusted. So, as I said, we're happy to give you personal advice. I'm excited about it, whether it's the old SK, the old Scania, or the old DAF. All of them have the same control system. So, as you've seen, we can optimize even the old ones. So, as I said, feel free to get in touch with us. So, I'll go ahead and say thank you very much for tuning in. I wish you a great day. Take care. See you next time. Bye.